Conservation laws in electrodynamics. Here we will discuss about conservation of charge and energy. So when we discuss about conservation of charge, there are two types of conservation, that is global conservation and local conservation. In global conservation law is that the total charge in the universe is a constant. But but when we deal with physics, the local conservation of charge is more important. That is treated as conservation of charge in the case of physics. Okay. Then what is conservation of charge, or what is called a local conservation of charge? It is nothing but if the charge in some region changes, then exactly that amount of charge must have passed in or out through the surface. In charge of some region, then the corresponding charge must have to pass in or out through the surface. So we know that what is charge Q of t can be written in terms of charge density rho. So Q of t is nothing but volume integral. So Q can be written as volume integral rho d tau. If the current is flowing out through the surface, then it can be written as closed integral j dot dA. So the change in charge dq by dt is equal to minus integral j dot dA, that is the current flowing out through the surface. So this is the charge conservation law. dq by dt, change in charge, is equal to minus closed integral j dot dA. If there is a change in in some region which is equal to the current which is flowing out through the boundary. So substituting for Q, we know that what is Q? Q is nothing but rho d tau. So this can be written as integral dou rho by dou t into d tau, that is equal to closed integral j dot dA. So using the divergence theorem, we can change the surface integral into volume integral. Then only we can integrate these two terms, because this is in the volume integral form and we have to convert this into volume integral form. So that is equal to minus del dot j d tau. So when we equate these two terms, we will get dou rho by dou t is equal to minus del dot j. This equation is very familiar for us. This is the continuity equation. So this is nothing but the conservation of charge. So next let us discuss about the conservation of energy. This conservation of energy theorem, otherwise known as Poynting theorem. So we already studied that the work necessary to assemble a static charge distribution, that is given by WE is equal to epsilon 0 by 2 integral E square d tau. And the work required to get a continuous current, that is the work against the back EMF, Wm is given by 1 by 2 mu 0 integral B square d tau. So this work done is stored as the energy in electromagnetic field. So the total energy stored in electromagnetic field per unit volume is given by U is equal to half epsilon 0 E square plus B square by mu 0. The work done by electromagnetic force on charge Q is given by F dot dl, that is equal to F is Lorentz force. So the force acting on electromagnetic field is Lorentz force, because there is an electric field and magnetic field. So that F is given by Q into E plus V cross P dot dl. dl is nothing but v dt. So when we do the dot product, the first when we examine the second term, it is v cross b dot v. This is a triple product, scalar triple product, and the same quantity is repeating, v cross b dot v. Its value is 0. So f dot dl is given by qe dot v dt. Now we are going to rewrite this equation. We are combine this q v dt together, and we are going to substitute it in terms of the current density J. In terms of rho and J, we know that Q is equal to rho d tau, charge density into d tau, you will get the total charge. So this QV is given by, what is Q? It is rho d tau into V. So this is nothing but the J d tau, the volume current density into volume d tau. Rho V is nothing but, rho is charge density and V is the velocity of that. So rho V is nothing but the current density. It is the volume current density. So rho V d tau can be written as J d tau. So we are going to substitute this J d tau in this equation instead of Q V dt. The rate of work done for all charges. This is F dot dl. So that is QE dot V dt, or it can be written as E dot J d tau into dt. So the rate of work done, that is dw, this is dw, here dw by dt is given by integral E dot J d tau. Or we can write, we know that del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. It is our fourth Maxwell's equation. That is the Ampere's law modified by the Maxwell as del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. We write this equation in order to get a term for E dot J. When we take a dot product with E, when we take a dot product with this equation, so E dot this equation, we have to take a dot product with this term and this term and this term. We have to take a dot product of E dot of this whole term. So if we do like that, we will get a term here E dot J. So from this term we can substitute here. Then we will get a meaningful equation. So for that we are going to write this Maxwell's last equation, and then we make a dot product with E, that is E dot del cross B, that is equal to mu 0 E dot J plus mu 0 epsilon 0 E dot dou E by dou T. E dot J is the work done. This is the work done per unit time per unit volume. E dot J is nothing but the work done per unit time per unit volume. So this is known as work per time is power. So this is power delivered per unit volume. E dot J is nothing but the power delivered per unit volume. So in this equation, what is E dot J? We will take this term and we know that what is del cross B. We will substitute for del cross B. Then we can write this as E dot J is equal to when we divide the whole term with mu 0, then we'll get E dot J. So E dot J is equal to 1 by mu 0. E dot del cross B minus mu 0 get cancelled from this last term. So you will get epsilon 0 E dot dou E by dou T. So when we find out this term will so our equation will become E dot J is equal to 1 by mu 0 E dot del cross B minus epsilon 0 E dot dou E by dou T. Now we are going to substitute for this term. Okay, 1 by mu 0 E dot del cross B. So we know that del dot E cross B, del dot E cross B can be written as B dot del cross E minus E dot del cross B. So this can be written as del dot E cross B can be written as B dot del cross E minus E dot del cross B. This term we want E dot del cross B. We are going to substitute for E dot del cross B from this equation. So we know that del cross E is equal to nothing but dou B by dou T. Del cross E is equal to minus dou B by dou T. So here minus B dot dou B by dou T minus E dot del cross B. So this E dot del cross B can be written as E dot del cross B. We take here this term on the left hand side. So you will get E dot del cross B, that is equal to minus B dot dou B by dou T. When this term will become minus del dot E cross B. Okay. So we know that B dot dou B by dou T can be written as half dou by dou T of B square. When we differentiate B square, you will get 2B dou B by dou T. 2B dot dou B by dou T. So it is nothing but 2 get cancelled. It is nothing but B dot dou B by dou T. So B dot dou B by dou T can be written as half into dou by dou T of B square. Similarly, E dot dou E by dou T can be written as half into dou by dou T of E square. Okay. So we can substitute for this term as half into dou by dou T of B square. Similarly, we can substitute this term. Our aim is to find out E dot J. So this term, when we look this term, this can be written as half into dou by dou T of E square. So we can write this as, we can write this to, when we include these two terms in our equation, so you will get this equation as this. E dot J is equal to 1 by mu 0 E dot del cross B minus epsilon 0 E dou E by dou T. So this we know that E dot del cross B can be written as 1 by mu 0 minus 1 by mu 0 B dot dou B by dou T minus 1 by mu 0 del dot E cross B, and this term is remains as such, that is minus epsilon 0 E dot dou E by dou T. So this term can be written as minus 1 by mu 0 B dot dou B by dou T minus epsilon 0, when we take this term to here, minus epsilon 0 E dot dou E by dou T minus 1 by mu 0 del dot E cross B. So when we combine these two terms, this we know that this is dou by dou T of this is dou by dou T of B square by mu 0, and this is dou by dou T of epsilon 0 E square. So when we combine these two terms, you will get this as minus 1 by 2, it is common, dou by dou T of epsilon 0 E square plus B square by mu 0, and this term remains as such, minus 1 by mu 0 del dot E cross B. And we know that dw by dt is equal to volume integral E dot J d dot, then substitute for E dot, this is E dot J, then substitute for E dot J, our equation will become dw by dt is equal to minus d by dt of volume integral half epsilon 0 E square plus B square by mu 0 d dot minus 1 by mu 0 closed integral E dot B dot dA. Here we apply the divergence theorem. Then the volume integral will become the surface integral. Okay. So S is the surface bounding the volume B, where S is the surface bounding the volume B. This is the volume term and this is the surface term. So this is known as the Poynting vector. Then we can write this equation as Poynting theorem is work energy theorem of electrodynamics. It is the work energy theorem of electrodynamics. This is the work done on the charges by electromagnetic force per unit time. This term is nothing but the work done on the charges by the electromagnetic force per unit time. So this term is the first term, that is half epsilon 0 is half epsilon 0 E square plus B square by mu 0. This is the total energy stored in the field, electromagnetic field. So this is the total energy stored in the electromagnetic field. And this term is the rate at which energy is transported out of the volume B. Okay, so these are the terms in the energy conservation equation of electrodynamics. So Poynting theorem is the work energy theorem of electrodynamics, and the first term on the right hand side is the total energy stored in electromagnetic field, and this can be written as U is equal to half epsilon 0 E square plus B square by mu 0. This is energy density. This is the total energy stored in electromagnetic field per unit volume. And the first term is integral U d tau, that is total energy stored in the field. And the second term is 1 by mu 0 surface integral, closed surface integral E cross B dot into dA. So this is the rate at which energy is transported out of volume across the boundary surface by the electromagnetic field. So we can write the work energy theorem as work done on the charges by the electromagnetic force is equal to the decrease in energy remaining in the field less the energy that is flowed out through the surface. In mathematical formulation, this can be written as this term, 1 by mu 0 equals B is known as the Poynting vector. So this is energy per unit area per unit time transported by the electromagnetic field. This is called the Poynting vector. So in compact form, the Poynting theorem can be written as dw by dt, that is equal to minus d by dt of integral u d tau minus the closed surface integral s dot dA, where s is the Poynting vector that is given by 1 by mu 0 E cross B. Thank you.